Imagine a metal so rare it's buried deep in the Earth's core, so valuable it outshines gold, and so powerful it drives the cars you ride, the jewelry you wear, and the clean energy of tomorrow. Welcome to the world of platinum, the king of metals, forged in a place where science meets spectacle, the mega factory. Picture this: thousands of tons of raw rock, blasted from ancient mines, arrive at a billion-dollar fortress of technology. This is no ordinary factory, it's a high-stakes arena where nature's toughest challenges are conquered. Massive crushers pulverize stone to dust, frothing tanks separate precious minerals, and roaring furnaces melt ore into rivers of molten fire. Every step is a battle of precision, where cutting-edge robotic arms, and lasers transform gritty ore into pure, shimmering platinum. But it's not just about power, it's about perfection. Each gram of platinum, worth thousands, takes a journey through explosive mining, high-tech flotation, and chemical wizardry to achieve 99.99% purity. From the depths of the earth to the catalytic converters in your car, the electrodes in your phone, or the fuel cells powering the future, platinum is the unsung hero of our world. Want to know how a dusty rock becomes a global treasure? Why does it take a mega factory's relentless innovation to unlock its secrets? This is a story of fire, science, and human ingenuity, a process so intense, so breathtaking, you'll never see platinum the same way again. Click now to dive into the heart of a mega factory and uncover the Platinum Odyssey. You won't look away.
What is platinum and its importance? Platinum is a rare, precious, and highly durable metal, renowned for its unique properties that make it indispensable in various industries. As a member of the platinum group metals PGMs, which include palladium, rhodium, iridium, ruthenium, and osmium, platinum stands out for its resistance to corrosion, high melting point, and exceptional catalytic abilities. These qualities make it a critical material in applications ranging from jewelry and automotive catalytic converters to electronics, medical devices, and fuel cell technology. The global demand for platinum is driven by its role in reducing vehicle emissions, powering clean energy solutions, and serving as a status symbol in luxury goods. However, producing platinum is a complex, resource-intensive process that requires advanced technology and large-scale infrastructure. This lecture explores the journey of platinum from its geological origins deep within the Earth to its final form as a refined product in a state-of-the-art mega factory, a facility designed for high efficiency, automation, and scalability. A mega factory for platinum production is a marvel of modern engineering, integrating cutting-edge machinery, automated systems, and stringent environmental controls to process thousands of tons of ore annually. This lecture will detail every stage of the process, from mining and/or concentration to smelting, refining, and fabrication, while highlighting the technological advancements that enable mega factories to operate at scale. We'll also address environmental and ethical considerations, ensuring a holistic understanding of platinum production in the 21st century. Geology and/or extraction, geological origins of platinum. Platinum is one of the rarest elements in the Earth's crust, with an average concentration of about 0.005 parts per million. It is primarily found in ultramafic igneous rocks, formed billions of years ago when molten magma cooled and crystallized deep underground. Platinum and other PGMs are typically associated with minerals like chromite, sulfide, and nickel-copper ores. The largest platinum deposits are located in South Africa's Bushveld Igneous Complex, which supplies approximately 70% of the world's platinum. Other significant sources include Russia's Norilsk-Talnakh deposits, Canada's Sudbury Basin, and smaller deposits in Zimbabwe and the United States. The Bushveld Complex, for instance, is a layered intrusion spanning thousands of square kilometers, where platinum is concentrated in thin layers called reefs, such as the Marensky Reef and Ujita Reef. These reefs contain platinum in the form of minerals like sperrylite task and cooperite PTS, often embedded in sulfide matrices. Understanding the geology, exploration, and mining, the journey of platinum begins with geological exploration. Geologists employ advanced techniques like satellite imagery, geophysical surveys, for example, magnetic and seismic studies, and core drilling to identify platinum-rich deposits. Core samples are analyzed in laboratories to determine PGM concentrations, often measured in grams per ton gram. For example, high-grade ores in the Bushveld Complex may contain 4 to 10 grams per T of PGMs, while lower-grade ores require more intensive processing. Once a deposit is identified, mining begins. Platinum is typically extracted through underground mining due to the depth of most deposits 500 to 2,000 meters. In some cases, open-pit mining is used for shallower ores, as seen in parts of Zimbabwe's Great Dyke. Underground mining involves sinking shafts and creating tunnels to access the Erebity. Techniques like stoping, removing ore in steps while leaving pillars for structural support are common. In a megafactory's supply chain, mined ore is transported to the surface via conveyor belts or rail systems and then trucked or railed to the factory, often located near the mine to minimize costs. A megafactory processing platinum might receive 10,000 to 50,000 tons of ore daily, depending on its scale. For context, a facility like South Africa's Impala Platinum processes millions of tons annually. Automated systems such as autonomous haul trucks and real-time ore tracking ensure efficiency. The ore arrives in large chunks, typically 10 to 50 centimeters in diameter, and contains only a small fraction of platinum 0.0005% to 0.001%, making subsequent processing critical. Ore processing and concentration, crushing, and grinding. Upon arrival at the mega factory, the ore undergoes primary processing to liberate platinum-bearing minerals. The first step is crushing, where large jaw crushers reduce ore chunks to smaller pieces to 5 centimeters. These crushers, often automated and computer-controlled, operate continuously, handling thousands of tons per hour. For example, a mega factory might use gyratory crushers capable of processing 5,000 tons per hour with sensors monitoring wear and tear to optimize performance. The crushed ore is then ground into a fine powder using ball mills or semi-autogenous grinding SAG mills. These massive cylindrical machines, up to 12 meters in diameter, rotate and tumble the ore with steel balls or the ore itself, reducing it to particles smaller than 100 micrometers. Grinding is energy-intensive, consuming up to 50% of a mega factory's power. Advanced mills incorporate variable speed drives and AI-based controls to maximize efficiency, ensuring the platinum minerals are exposed for subsequent separation. Froth flotation. The ground ore, now a fine powder, is mixed with water and chemicals to form a slurry. This slurry undergoes froth flotation, a cornerstone of platinum processing in mega factories. Flotation separates platinum-bearing sulfide minerals from non-valuable gangue waste rock. Chemicals called collectors, for example, xanthates, are added to make PGM minerals hydrophobic, while frothers create stable air bubbles. The slurry is pumped into large flotation cells where air is injected, causing the hydrophobic PGM minerals to attach to bubbles and rise as a froth. A mega factory might have banks of flotation cells, each holding 100 to 500 cubic meters of slurry, processing thousands of liters per minute. The froth, rich in PGMs, is skimmed off and dried, producing a concentrate with 100 to 500 grams per T of PGMs. Non-valuable minerals sink and are discarded as tailings, often stored in engineered dams with environmental monitoring systems. Some megafactories use secondary flotation stages or gravity separation, for example, spiral concentrators, to recover additional PGMs, increasing yield. Transforming ore into matte. Once the platinum-bearing ore has been concentrated into a PGM-rich powder through crushing, grinding, and froth flotation, the next stage in a mega factory is smelting. Smelting involves heating the concentrate to extremely high temperatures to separate valuable metals, platinum, palladium, nickel, and copper from waste materials. In a mega factory, this process is conducted in large-scale, automated furnaces designed for efficiency and continuous operation. The concentrate, which typically contains 100 to 500 grams per T of PGMs along with sulfides of nickel and copper, is fed into electric arc furnaces, EAFs, or flash furnaces. These furnaces operate at temperatures of 1400 to 1600 degrees Celsius, melting the concentrate into a molten mixture. A megafactory's smelting facility might house multiple furnaces, each with a capacity of 50 to 100 tons of concentrate per batch. For example, a facility like Anglo American Platinum's Polokwane smelter in South Africa processes thousands of tons daily, using furnaces up to 20 meters long. The smelting process produces two primary products: a molten matte rich in PGMs, nickel, and copper, and slag, a waste product containing silicates and other non-valuable minerals. The matte, which is denser, sinks to the bottom of the furnace, while the slag floats and is skimmed off. Megafactories employ automated tapping systems to drain the molten matte into ladles, which are then cooled into solid blocks. The slag is either discarded in environmentally controlled tailings dams or reprocessed to recover residual PGMs. The first step is to dissolve the matte. The matte ingots or granules are crushed into a fine powder and treated with aqua regia, a mixture of nitric acid NO and hydrochloric acid HCl in a 1:3 ratio. Aqua regia is one of the few reagents capable of dissolving platinum and other PGMs. In a megafactory, this process takes place in large, corrosion-resistant reactors, often made of titanium or glass-lined steel with capacities of 1,000 to 5,000 liters. The reactors are equipped with automated stirring systems to ensure uniform dissolution. The dissolution produces a solution containing platinum, palladium, rhodium, and other metals as chloride complexes, for example, chloroplatinic acid, HFTLC. Base metals like nickel and copper are also present, requiring separation. The solution is filtered to remove undissolved residues, and the filtrate is pumped to the next stage. A megafactory might process thousands of liters of solution daily, with automated pumps and pipelines ensuring continuous flow. Precipitation and separation. To isolate platinum, the solution undergoes selective precipitation. Ammonium chloride NaCl is added, causing platinum to precipitate as ammonium chloroplatinate NaCl, a yellow-orange solid. This precipitate is filtered out using high-capacity vacuum filters, leaving other PGMs like palladium in the solution for separate recovery. The filtration systems in a megafactory are automated, with sensors monitoring particle size and purity to optimize yield. The ammonium chloroplatinate is then heated in a controlled furnace 600–800 degrees Celsius to decompose it into a platinum sponge, a porous metallic form. This step, called calcination, is conducted in induction furnaces with precise temperature control to prevent contamination. A megafactory's refining plant might have dozens of such furnaces, each processing 10 to 50 kilograms of platinum sponge per batch. Advanced refining, solvent extraction, and ion exchange. For ultra-high purity, megafactories use advanced techniques like solvent extraction or ion exchange. In solvent extraction, the platinum-containing solution is mixed with an organic solvent, for example, tributyl phosphate that selectively binds to platinum ions. The solvent is then separated, and platinum is stripped back into an aqueous phase for further processing. Ion exchange involves passing the solution through resin columns that selectively capture platinum ions, which are later eluted with a stripping agent. These methods achieve purities of 99.99% or higher, meeting the stringent requirements of industries like electronics and catalysis. Megafactories integrate automated chromatography systems for ion exchange with real-time monitoring to ensure consistency. The refined platinum is melted in high-frequency induction furnaces and cast into ingots, bars, or granulated into powder, depending on the end use. Megafactory refining infrastructure. A megafactory's refining facility is a high-tech environment with clean rooms maintaining ISO Class 5 standards, fewer than 100 particles per cubic meter. Robotic arms handle hazardous chemicals, while automated systems monitor pH, temperature, and flow rates. For example, a factory like Johnson Matthey's Refineries uses computer-controlled reactors to process thousands of kilograms of PGMs annually. Waste solutions from refining are treated to recover residual metals and neutralize acids, ensuring environmental compliance. Quality control and testing. Partial assaying for purity. Once platinum is refined, it undergoes rigorous quality control to ensure it meets industry standards, for example, 99.95% purity for catalytic converters or 99.99% for electronics. In a megafactory, quality control is fully automated using advanced analytical techniques. The primary method is fire assay, where a sample of platinum is melted with lead and fluxes to separate impurities, then analyzed for PGM content. X-ray fluorescence XRF spectroscopy is widely used for non-destructive testing. XRF analyzers, integrated into the production line, scan platinum ingots or powders in seconds, providing a detailed breakdown of elemental composition. Inductively coupled plasma optical emission spectroscopy (ICPOES) is another technique offering higher sensitivity for trace impurities. A megafactory might test hundreds of samples daily, with automated systems flagging any batches that fall below specifications. Automated quality systems, megafactories employ AI-driven quality assurance systems to streamline testing. For instance, machine learning algorithms analyze XRF and ICPOES data to predict batch quality, reducing the need for manual checks. If a batch fails, it is automatically rerouted for reprocessing. These systems ensure consistency, which is critical for applications like fuel cells, where impurities can degrade performance.